and welcome back. We are in the midst of determining a rate law expression given experimental data. So let's try one more of these. We have an equation, and do not use A and B when you are given actual chemicals. You must use the chemicals. So we're going to start with the generic, and we find it's possible that the rate is equal to K. Sorry, that should be a times. Let me rewrite that. K times the concentration of carbon monoxide to some power times NO2 to a possibly different power, where X and Y are the order and can be 0, 1, 2, or maximum really 3 is what you should see. Now, to find the order with respect to CO, we want the constant concentration of NO2 to be constant or controlled. And so if we look through our data, we find that between trials 4 and 5, CO changes, NO2 does not. So we're going to take a ratio of these generic rate laws. If you put the largest rate on top, your math will be easier. So I'm going to put trial 5 over trial 4. 6.8 times 10 to the minus 8 is equal to, now we've plugged into the generic rate law. So we have K. Remember, K is not known yet. So we have K. Now, in place of carbon monoxide, I'm going to put 1.5 times 10 to the minus third to some power. And then I'm going to put in for the nitrogen monoxide. Now, if you don't write this part down, the things that are constant, I'm okay with that. If you didn't write this or this because you knew you picked them so they would cancel, I'm fine with that. I just like to write them to just make that explicitly clear what I'm doing here. 0.35 times 10 to the minus fourth to the y. So now we cancel. So if you had not written that down or that down, if all you had written was this and this, I would still give you credit for your work. But you have to show minimum that much. So if we solve for this, we get 1.5 is equal to 1.5 to the x. Hopefully it's self-evident that x is equal to 1. Therefore, we say it is first order with respect to the concentration of carbon monoxide. Okay, let's try the next one. What is the order with respect to NO2? Well, we're going to do the same thing. We're going to take ratio of rate laws, and we want this time our concentration of carbon monoxide to be constant or controlled. Okay, now that happens between here and here. I mean, it also happens between 3 and 2 and 1 and 3. So any of those will work. Any place where this is constant and this varies will work and get you the value you need. So I'm going to put my large number or large rate on top of the small rate, so I'm not dealing with fractions. And that way, hopefully my order will be self-evident. So I have K over K. If you don't write that, you wouldn't get it wrong. 5.1 times 10 to the minus fourth times 0.7 times 10 to the minus fourth. That's trial 2. 5.1 times 10 to the minus fourth. Okay, and we know that's to the first power. So honestly, if you couldn't find some place where these were constant or controlled, just keep them in the algebra. The only reason we had to have them cancel before is because we didn't know the power. So 0.35 times 10 to the minus fourth. That cancels and that cancels. And you should get 2 is equal to 2 to the y. Sorry, I forgot my y powers there, right? 2 is equal to 2 to the y. Y is equal to 1. That means it's first order with respect to your concentration of NO2. Now let's write the rate law expression. Rate is equal to K. Temperature independent means we haven't specified a value for K. Do not put A's and B's in here if you have real values. Sorry, that's a 1. I was talking It's like talking and walking at the same time. Apparently I can't talk and write at the same time. Carbon monoxide to the first, you can put a 1 there, but that's implied. And NO2 to the first power, right? So we're partway done with this. Now what we want to do is find the value for the rate constant. So we have rate is equal to K times carbon monoxide times NO2. We know those powers. You can choose any one of those. Any of that data will work and get you within experimental error the same value for K. I happen to have chosen 5. So 10.2 times 10 to the minus 8 is K times 1.5. I'm plugging in for carbon monoxide, and that's to the first power. 0.35 times 10 to the minus 4, also to the first power. Cross multiply, and voila, through the magic of algebra, you should get K is equal to 1.9. Now, let's take a look at units. Remember, it's time, so look up here and grab your time factor. So it's time to the minus 1. That's the same thing as saying 1 over hours. And then it's concentration to the minus. You take the overall order. The overall order is 1 plus 1. That's the overall order. And then we take away 1. We want all of the molarities to cancel except 1. So that gives us hours to the minus 1, molarity to the minus 1. So, or another way to say that is 1 over hours times molarity. So our temperature dependent would be rate is equal to 1.9 times CO. Rate law expressions don't have molarities plugged in. It means symbolically speaking. When you see the word expressions, it means a symbolic representation of that. So that is another one of these. We could go on and plug in values here into that rate law. We know K now. If you plug those values in, I'd like you to try that. You'll get 3.4 times 10 to the minus 5th. All right. Now I'm going to be skipping this one. I'm going to let you do this one, but you will find that one of these has a 0 order, which means that rate doesn't change when I change that concentration. It's not involved in the important step of a mechanism. So that's going to be it for rate, other than all the wonderful ones we'll do in class. The next video will touch on equilibrium. So until then, this is your best chemistry teacher. Okay, I'm your only chemistry teacher, but I'm still your best chemistry teacher. Signing off.